So we're going to talk about magnetism now, and the so magnets, have certainly been known since even before the time of the Greeks. There were certain stones that exhibited exhibited magnetism. And a lot of times people found that those stones contained iron. They can also contain nickel and cobalt, we now know. And these are what are called ferromagnetic materials. There's certain metals that tend to become magnetic. Other metals tend to not become magnetic. For example, copper. It's very difficult to magnetize copper or aluminum. All right. So, all right. Magnets have, of course, two poles. You don't talk about, like with the electric field, you talk about the charges. They have a magnet has a north and a south pole. The field lines go from the north to the south, just like the field lines in an electric field go from the positive charge to the negative charge. But this is different. It's a different phenomena. And let's see. So one of the things that people noticed is that if you take a permanent magnet, like this bar magnet right here, and if you break it in half, you get instantly two new magnets. And so when you break this larger magnet in half, you're going to get a south pole, and on the opposite end of where the original north pole was, and a north pole in the opposite end where the original south pole from where the original south pole was. And if you break the magnet again, you'll get a bunch of smaller magnets, and so on, and it keeps going. And so this is this idea of having both poles is actually very different than electric fields. For example, you can have a single positive charge and really put it anywhere in the universe, and there doesn't have to be a negative charge anywhere near it for there to be an electric field. But for a magnetic field, there's always a north and a south pole. We've tried, actually, lots of experiments over the last 50 years to find a single north pole or a single south pole. They're called magnetic, they have a name, they're called magnetic monopoles, but they don't seem to exist. At least right now, all the experiments show that they don't. All right, so one of the nice things about this magnetism is until we get to transformers, there's not a lot of math involved. So, and of course, let's talk about this: the fact that like poles attract. I'm sorry, opposite. Like poles repel each other. A north and a north will repel, and unlike poles attract. A north pole and a south pole will attract each other. And So this is actually how compasses work, right? A compass, the north pole of a compass points to the magnetic south pole, well, you might, if you think about that, there's that has to do with. Whoops, let me go back. Hold on. Whoops, sorry. Oh goodness. So what that tells us is at the North Pole of the Earth is actually the geographic North Pole. There's actually a magnetic South Pole, and that's why compasses point north, right? Otherwise, a compass simply wouldn't point north. All right. So moving on. So where do magnetic fields come from? And the simple answer is charge, moving electric currents. Okay, sorry, not charge, but moving charge. So electric current is what causes magnetic fields. And so there must be, if you think about the Earth, for example, the fact that the Earth itself has a magnetic field, there must be some kind of electric currents running around inside of the Earth. And we think that has to do with the outer molten core of the Earth, the outer liquid core. For permanent magnets, it's a little bit more complicated. The spin of an electron will cause a little magnetic field, and many electrons will cause a much larger overall magnetic field, and we call these magnetic domains when a bunch of the spins line up to make an overall magnetic field. And if we were to look into a ferromagnetic material, like for example a piece of iron, you find these little magnetic domains, but when the piece of iron is not magnetized, they're pointing in all sorts of different directions, like this one right here. When they're exposed to some external magnetic field, these little magnetic domains will tend to line up. Not all of them have to line up, but just when most of them line up, then that's this. And then you take away this external magnetic field. Most of these domains will line up, and that makes a permanent magnet. And some of these materials will hold that magnetic field for a very, very long time. Not forever, but for a long time. So, this is what we were talking about with the Earth. So notice the Earth acts like a giant bar magnet, where the south magnetic pole comes out really close to the North Pole. Not exactly at the North Pole, but by the way, it's actually comes out in northern Canada, and similarly, the magnetic North Pole of the Earth comes out towards the South Pole. And we know from volcanic activity and the fact that the direction of the poles, it gets frozen as the lava cools. We know that in fact that the orientation of the Earth's magnetic field has changed over geological time. So here's this is the last reversal, so this is not even a million years ago, so 780,000 years ago, we have evidence that there was a reversal where the north magnetic pole came out right here, and so compasses, which of course weren't around back then, but compasses would have pointed to the South Pole then. All right, let's move on. This is what's called the magnetic offset or magnetic declination, and so depending on where you are on the Earth, the North Pole of a magnet doesn't quite point north. So this is just telling you the different, how far off a compass would be from actually pointing to true north. So like along this line here, you're actually pointing at true north, and then anyhow, that's not that important. All right, so moving charge produces magnetic fields. There was a guy named Ørsted who made this great discovery back in the year 1820 that current or moving charge creates a magnetic field, and it actually creates a magnetic field that goes in a circle. So on this platform here, you can see the magnetic field. It's actually a three-dimensional thing. So there's a magnetic field up here and down here. So as the current moves, it's creating as the charge moves, which is what current is, it's creating a magnetic field. And so what Ørsted discovered is that anywhere he placed the compass would would make, basically form a circle overall. And so some people after Ørsted's discovery in the year 1820 started playing with the wires and forming different magnetic fields, or different with different geometries. They could create the different shapes. They noticed if they curled, or if they made a circle, the magnetic field kind of looked like instead of like a horseshoe magnet, it looked more like a bar magnet, which is what this is showing. And some people a little bit later on found that if they made many turns, and this of course has its own name, when you have many turns of coils so the current runs through this all these coils, and they're all curled and the current runs along in the same direction. This, by the way, is called a solenoid. If you've ever had to have the solenoid in your car replaced, you've probably heard that term before. This is actually what gets your car started, believe it or not, when you turn the key, and the whole large amount of current runs through here, and that creates a very enormous, very strong magnetic field for a short time, and that basically causes a bar of iron to move suddenly, because all of a sudden there's a very strong magnetic field, and that bar of iron is of course mechanically coupled to the engine, and that causes the pistons to start to move up and down, and then then the cylinders start firing because there's gas and air mixture, and you no longer need this, and because the pistons are moving up and down, from gasoline and air exploding. All right, so that's a solenoid. Let's see. These are just different applications. I'm going to quickly go through this. You can actually measure, of course, voltage and current. This is an example of an electric meter. When it's measuring voltage, that's called a voltmeter. When it's measuring resistance, it's called an ohm meter. An ammeter is for measuring current. Another thing that's used very often is having a relay. For example, when for like thermostats, for example, you want the thermostat coming on, and when the house warms up a little bit, it'll cause this bimetallic strip. If you go back to the chapter on heat, this will expand, and it'll cause an electric contact to be made, and that you during the summer, for example, you want the air conditioning to come on when the heat gets too high, and so forth. So we use these as switches. It's used these are also used as speakers. They're also used as microphones. There's a lot of uses for magnetism. And there's also electric motors, which basically turn electrical energy into mechanical energy, into motion. So this is an example of that. And then we come to what's called electromagnetic induction. So going back to the time of Ørsted, remember, electric current can create magnetic fields, and so people wondered, do magnetic fields create electric currents? And this discovery happened around 1832 by a guy named Faraday. All right, we'll go into that in the next video.